In this lecture, we will talk about water resource theory design fundamentals. Water resource has two main types, surface water and groundwater resources. Groundwater with their properties are the most suitable water resource for drinking purposes, while surface waters are easily available, often in an amount exceeding the groundwater resources, but their quality is getting worse, requiring costly water treatment. Structures designed for withdrawal of water of groundwater resources may be divided into two main groups: vertical and horizontal. Vertical could be like shaft, tube drilled wells, and radial wells, while horizontal are collection gallery, collection tunnel, and shallow placing of an aquifer from 5 to 7 meters with smaller thicknesses. A spring chamber are spring capitation structures that catches the springs flowing freely, ascending to the earth's surface. Springs are found mainly in mountainous or hilly terrain. A spring may be defined as a place where a natural outflow of groundwater occurs. Spring water is usually fed from a sand or gravel water-bearing soil formation called an aquifer. For instance, a region in Central Europe, Slovakia, where I live in, the main source of drinking water is groundwater resource, while, for instance, Austria has spring water as the main resource for drinking water. Structures designed for obtaining of water from surface resources, like from watercourses, ponds, lakes, reservoirs, may be divided according to the type of the water resource into withdrawal of water from watercourses, mountain streams, rivers, channel capitation devices, while for river basins, the capitation devices is a part of the weir body. For dam reservoirs, the capitation device is a part of the dam construction or a separately standing object. Water resource yield is the amount of water which a water resource can provide per time unit at a given moment. Moving on. Then we're going to be speaking about seepage or filtration spring. The term seepage refers to springs with small flow rates in which the source water has filtered through permeable earth. Artesian overflow springs often have a large recharge area, sometimes a great distance away. The water is forced out under pressure. The discharge is often considerable and shows little or no seasonal fluctuation. Artesian springs have the advantage that the impervious or impermeable cover protects the water in the aquifer against contamination. The water from these springs is usually bacteriologically safe. In general, spring water is of good quality. One of the key signs of a good spring is that the water maintains a constant temperature throughout the day. This temperature is just below the average air temperature. The water should also be colorless. Variation of the water temperature during the day and coloration of the water shortly after rains are indication of a poor quality spring source. Yield measurement. The quantity of water a spring produces is known as its yield. Information about the yield is crucial in decision making for the tapping of a spring. Water resource yield is the amount of water which a water resource can provide per time unit at a given moment. Various methods for measuring the water resource yield is by using flow meter for a smaller amount of the water, or by using weirs. We have two main types, Thomson and Poncelet weir. Thomson's weir is basically indicated by this formula, which is 8/15, coefficient U square root of 2g, h is the height of the weir to the power of 5/2. While Poncelet's weir, look here, much more horizontal, and the equation is usually indicated by Wasbach formula, which is 2/3 of the coefficient U times B, the width of the weir, square root of 2g, h is the height of the weir. Design of a spring. The major components in the design of a spring source water supply system include the actual spring water collection area, where the water from the aquifer is actually being channeled to a discharge point with a supply pipe, the collection gallery, collection tunnel to the accumulation chamber, spring chamber, and the outlet to a storage tank. So this is the spring captation structure from the collection gallery to the it goes all the way to the accumulation chamber, which is here Poncelet's Weir. Here, wells are divided into wells with unconfined and confined water levels. Wells with unconfined levels are the ones that are built in the rock environment, where the underground water level is not confined by a waterproof level from above, like an impermeable material. Wells with confined level are in the rock environment, where the underground water stream is confined both by impermeable bedrock from below and by waterproof layer from above. Water is under pressure, and when the well is drilled, the water rises up until the pressure of the water column is balanced with the pressure of the confined level of the underground, also called artesian wells. This is an example of a well in reality. So he's using a bucket in order to obtain water, as you can see. Alright. So these are the two main types of wells: artesian wells and unconfined well. This is the water table: unconfined aquifer, upper confining bed, artesian aquifer, low confining bed, and a consolidated rock. Both types of wells with confined and unconfined water levels are divided into wells completely penetrating the aquifer, as we can see here, or partially penetrating the aquifer, which is an incomplete well, as we can see here. According to the methods of the well construction, diameter and depth wells are divided into tube drilled wells and shaft dug wells. Tube wells are also called drilled wells. They are made by drilling. They allow for the withdrawal of water from greater depth and larger areas, while shaft wells are suitable for the abstraction of water from lesser depth. They are designed maximum up to the depth of 15 meters. Their construction to greater depth won't be economical. The diameter of shaft wells is from 1 meter to 6 meters. So we can see also here, this is my clay seal, this is my water table, drawdown, water level, unconfined aquifer is here, and this is my perforated well screw. Also the shaft wells has the same. This is my claw seal, water table, drawdown, water level, unconfined aquifer, and impermeable layer. And we can see that they have here lesser depth, and their construction is not economical when it comes to larger depth or greater depth. Complete well with unconfined water level. So the yield capacity of a well completely penetrating an aquifer with unconfined water level is calculated by this formula, which is called Dupuit's formula. This formula indicates Q as the yield capacity of the well, pi times K. K is my filtration coefficient. H squared is the height of unconfined aquifer above the bottom of the well, minus H squared is the drawdown water level during pumping of Q, divided by the logarithm of R, which is the radius of influence of the water level drawdown during pumping Q, over R, which is the radius of the well. Okay, so we can see here also in this equation that this is my R, which is the radius of influence of the water level during pumping. Small r, it is the radius of the well, which is inside here from the dashed line all the way to this line, thick line. K is my filtration coefficient depending on the type of the soil that we have, and H is here, this part all the way from the unconfined aquifer above the bottom of the well, so all the way from the bottom to the top is my H. So when Dupuit was deriving his calculation for the yield capacity of the well, he followed from theoretical assumptions of isotropy, which means equal characteristics in all directions, and homogeneity of the aquifer. The aquifer also has an unlimited area. A well is building up to the impermeable layer. While the water is pumped from the well, the contour lines around it get a shape of concentric circles, with the common center in the axis of the well. Empirical Sykrat's formula is shown here. So this formula shows when drawing the water from the pump in this originally horizontal underground water level, a cone of depression, also called a drawdown curve, is created. the radius for which is r. So this is my cone of depression, or also called the drawdown curve. So this is the radius which is r. 3000 times z. Z is my water level drawdown, times k, which is my filtration coefficient. This is schematically presented a well completely penetrating the aquifer with unconfined water level. The line of yield capacity, this is my line of yield capacity, Q, is calculated by the Puig formula for different values of Z drawdown. So this is my different values of Z, and this is my drawdown Z, this is my line of yield capacity, and this is my Q. And also this is my water table, this is my Z1, Z2, Z3, this is my H. So the validity of the yield capacity formula is limited by maximum flow speed around the wells per meter Vmax, which the water may reach in the given aquifer. Based on many experiments, Socrates determined the maximum filtration velocity Vmax by the empirical expression here. So Vmax is equal to the square root of K over 15. The amount of water pumped from the well at a maximum flow speed Vmax is called the specific capacity of the well. Specific capacity is the amount of water which can be pumped from the well at the maximum entrance velocity, so that no particles are brought into the well from the aquifer or the gravel pack. So this is the equation of the specific capacity that we're going to be using. 2 pi times r, radius times h, height times k, coefficient, divided by 15. The specific capacity increases proportionally with the area of the well through which the water flows into it. In the intersection point of both curves, the yield capacity is equal to the specific capacity. This point gives the optimal amount of water pumped from the well. So the intersection of the line of yield capacity that we've seen here and the line of the specific capacity gives this point, and this point is called the optimum capacity. According to Socrates, the most economical drawdown in the well is Z is equal to H over 3, where H is the height of the aquifer above the bottom of the well.